the last session, we continue on the methane industry and methane measurement. I will share this session. My name is Olivier Duclos from Total Energy. I'm in the R&D team. So we will speak after of not only of oil and gas, but we will see after the pitch this morning of IMEO. We will have now the data, and after we will, if the remote discussion will work, we will have some information about biomethane, and the last presentation will be on the coal emission. So, if you are ready, we will start with James France. He works in EDF. So the floor is yours.
Thank you very much. Apologies for some of the slides. It appears that I've done mine in 4:3, and then they're going to be presented in 16:9. So I only have myself to blame for that. Right. Lovely. Okay, so I'm going to give us a little bit of an overview of some of the science studies that we've been doing within IMEO and previously under the banner of CCAC that are now managed by IMEO. So I work for the Environmental Defence Fund, and I'm on the Scientific Advisory Committee to the Scientific Oversight Committee of IMEO. So what's the rationale for our work within IMEO? Well, this has already been talked about plenty already today, so I won't hang about. But we're essentially looking at the oil and gas industry as an excellent target for emission reduction. Potentially, we're looking at around 70% of emissions that could be reduced, and about 40% of that could be done in a cost-effective manner. So it seems like that we can get some industry buy-in and hopefully convince people that that's something worth chasing. We've seen this graph already before, and if I can just get my pointer working, you can see there that the abatement potential of around 68% for the oil and gas industry, but also through IMEO, we're now looking at the coal industry a little bit as well, as you've already heard. And what are we really focusing in on? Well, we're looking really at the keys to good mitigation. As well as direct action, what we absolutely need to know is where the emissions are, what the quantity of the emissions are, and then, as been brought up already quite a few times, we need ongoing monitoring to be able to assess whether those emissions reductions are happening and how well they are happening. So the goal of IMEO, we are aiming to close the knowledge gap in both the location and the magnitude of the methane emissions. And we're doing this through, as been already explained, through a series of peer-reviewed studies and the reconciliation of measurement data. So there's two things really that I think you can say are missing within our scientific understanding. One is our geographical coverage. As you see, most of our emissions monitoring and focus in scientific studies has been predominantly in North America and in Europe, but it doesn't take too much of looking at this map to see that there are huge swathes of the oil and gas industry that are currently poorly studied, whether that be Africa, the Middle East, Southeast Asia, and such like as well. But that's also not to forget that it's not just a geographical problem, it's also a process understanding problem. So we may know very well that we have emissions, but knowing exactly where those emissions are coming from within a site may be actually very poorly constrained. So this is a study from the US, where you can see that the actual emissions measured do not match up at all with the greenhouse gas inventory assumptions, and that can go both ways in terms of over-emission or under-emission. So tightening this up so that we have a much better understanding is also of utmost importance, not just so that we get our inventories right, but also that we can target the mitigation where it actually needs to be. So this is what we are currently doing, or has previously been going on within CCAC and IMEO. We have various studies that have already been going on. whether that's been in the Gulf of Mexico or within the Permian Basin over here, city-urban studies in Europe, as we've heard already today, flight studies over in the North Sea, or the large CCAC project over with Romeo. And then we have various other projects that are now in the late stage planning campaign, planning stage, or within the actual undertaking already and getting action. So they include, we're currently looking at production in Colombia. We've got offshore work going on down in West Africa. We have a series of abandoned well projects. We have Oman as well, Azerbaijan rather, and Oman. And these are all sort of giving you a flavour of the type of work that we are looking at. And as Manfredi was saying earlier, we will have a portal open for suggestions for future projects and future studies that people may be coming up with and like to contribute to. So first of all, we'll have a quick look at the abandoned oil and gas wells project. So I'm going to give a snapshot of 3 studies that have been done at, or either ongoing or have been completed through this process, and go through different scales. So we'll start with the oil and gas project, the abandoned wells project, where we're looking at chamber measurements. So we're starting at the really small scale, looking at individual wells. So this is PI'd by Mary Kang over at McGill University, and we have a series of co-Is, but Monia Prosecki has helpfully handed over some images as well, so I can show you things. But this is essentially what we're looking at on the ground. We're looking at old wells, having to search them out, encase them, measure fluxes. So it's a very labour-intensive process, and it's very much a drop in the ocean when you think about what the total number of abandoned wells are estimated to be in the world. So this is very much an estimate, but this is based on Mary Kang's work already in the US. She's put a number of 2.5 million abandoned wells in the US alone, and has upscaled that to a very rough estimate of maybe 20 million abandoned wells globally. We've currently measured about 700 in the literature so far, so that might give you an idea as to how much we're really scratching the surface of this as a potential problem. And fundamentally, there's very little measurement outside of North America. So there's little bits here and there, but nothing too much in the scientific literature. How is this being done? So what is being done with these in North America is that these custom chambers are being built to fit over different types and different sizes of wells. Entirely different chambers if there are underground wells that are effectively having to be dug out. And as you can see, it doesn't necessarily look like the most sort of high-tech solutions to these things, but you'll encase the well and simply allow the methane to build up inside the chamber and measure the emission over time and calculate a flux rate that's individual for each well. So that can give you an idea as to how labour-intensive this might be. Sadly, my video is not going to work for the next slide, but this is work from Italy, and they have asked me to keep the location confidential for the moment. This is work that's hopefully will be published late this year. There are huge vents of unplugged well shafts in Italy that are spewing. This should have been a nice FLIR video. Unfortunately, it's not going to play. But the order of the flux is in tons or tens of tons a year from a single shaft. So these are our equivalent of super emitters for our abandoned wells. So the big question is, how many of these exist? Can we develop a way of working out where they are likely to exist? Can we do something statistically significant to work it out? And then the final challenge is going to places like Azerbaijan, where we have a combination of ongoing process and abandoned wells within the same structures. within the same fields. So this presents a whole different type of measurement problem and dynamic to go and work in. Secondly, I'll chat about the Australian coal seam gas from the Surat Basin. This is thanks to Bryce Kelly mainly, and also from the Jörg Hacker and Bruno Neinringer from the Airborne Research Australia. And for those of you who aren't aware of where the Surat Basin is, we're over here in Australia, next to Brisbane, up in Queensland. And it's responsible on paper for about 3 to 4% of the Australian methane emissions in total. It's currently still under development, and we're looking at 20,000 coal seam gas wells and its associated supporting infrastructure when complete. What does this look like? So you'll get a nice series of pictures now showing you what we're looking at in Australia. Essentially, we're looking at a whole series of well pads spread out right across the basin, which in itself will be a challenge to go and measure just on sheer scale and size. But there's added complexity because we have various processing plants and such like within the system. We have water holding ponds, pipelines, and such like as well. But then on top of that, as you may be aware, in Australia, there are some absolutely enormous cattle feedlots as well, emitting methane quite happily. And there might be other problems as well, such as large termite populations emitting methane. So there's lots and lots of things all intermingled together, making flux estimations rather challenging. So what we have got a combination of mobile methane studies, so drive-arounds, which have gone on essentially just before the aircraft campaign to identify at ground level where all our methane sources might be. So here we have a drive-around, so a vehicle survey essentially, and all these little dots are where we've been able to identify different types of methane emissions, ranging from the raw water ponds associated with the CSG to the coal mines, to the cattle feedlots, to the CSG plants, various problems with abandoned wells and such like as well. So it's an incredibly complex problem. As Anka alluded to earlier with the style of measurements, very similar. We've got a light glider-style aircraft equipped with a Los Gatos LGR methane CO2 analyzer, and they've run upwind, downwind flight tracks of various component parts of the CSG infrastructure. 13 science flights over 15 days, and what we end up with is this classic box model, but it's a classic box model with a huge amount of problems, because then we also have to try and account for all the emissions from things that are not just methane from the coal seam gas infrastructure. So they've tried to account for the cattle feedlots and such like as well, and come out with a total estimate of the CSG sources emitting of about 0.4% of the produced gas, which is a little bit higher than the existing inventories allow for. I've got 2 minutes, so I'll very quickly mention the Gulf of Mexico as well. So this is our colleague Daniel Zavala, who's provided me with this data. And what we can see here is it's a study of onshore and offshore assets in the Gulf of Mexico. Here we can see these spiral-style surveys done in the scientific aviation sort of method, where we have an upwind curtain and a downwind curtain, and we're able to deduce the mass of methane that has crossed across from each piece of infrastructure. And what we've been able to do then is interrogate the satellite data alongside this, and also the flaring pictures as well. And what was quite surprising from this is that the oil and gas infrastructure inventory for the offshore was dramatically overestimating the emissions, but the onshore was chronically underestimating the emissions. So what we've ended up with is an oil and gas loss rate of about 4.3% from the region, which is quite large and concerning in itself, but also a huge mismatch between the declared inventory for the offshore and for the onshore numbers. So that just about rounds it up, and just to bring it all back to IMEO. So this is where the scientific studies are slotting in to these direct measurements as part of the IMEO data sets. But as Manfredi chatted about before, it's not just the science studies that are going into IMEO. It is a huge collection of data going all the way through from inventories to OGMP to the satellites to give us this holistic look so that we can interrogate this future down the line and create something that is worth more than these individual studies on their own. Thank you very much.
Thank you, James, for your presentation. You remind us the responsibility of oil and gas after with the time when we are not in production. We need also to take care about the oil patch. Message is clear. So next we will speak of biomethane with Semra Bakkaloglu, I hope, from Imperial College. So she's not here, but we can work in a remote session. Is it okay? Okay. So let's go.
On how much methane is released in the biomethane supply chain. On behalf of the other co-authors, Jaroslaw Necki and Adam House, this study titled Methane Emissions along the biomethane and biogas supply chain are underestimated is currently in press at One Earth. On June 17th, it will be available online. Please don't take any pictures. We are in the embargo right now, and after the June 17th, we all have the study. Let me begin with the overview of my presentation. After a brief introduction to biomethane and biogas production, I will describe the methodology used in this study, and after sharing the findings and discussion, I will conclude my presentation. Let's start with the introduction. As we move further into the 21st century, the energy system must away from fossil fuels and grow in renewable energy capacity if Paris Agreement targets are to be met. However, due to the challenges in adopting low-carbon technologies, certain areas of global energy system are difficult to decarbonize, such as heavy industry, transport, heating and cooling system, which together account for a significant proportion of carbon dioxide emissions. Natural gas has therefore been used as an important alternative fuel with much lower carbon dioxide emission compared to coal and oil. However, we know that the natural gas emits large amounts of methane. An alternative method of decarbonizing natural gas is we are replacing it with biomethane or biogas, which is a mixture of gases, mostly methane and carbon dioxide, produced from biodegradable materials such as crops, animal manure, municipal salt waste, or sewage sludge. According to the International Energy Agency, IEA, the global biomethane and biogas production could meet nearly 20% of global gas demand if its sustained potential was fully utilized, and 35 million tons of oil equivalent biogas and biomethane were used globally in 2019. As the graph shows, the majority of the production comes from Europe. However, recent studies show that the biomethane and biogas production facilities can also emit methane. These studies have measures on-site and off-site measurements. On-site means measurements of emissions at individual point sources, and off-site means that measurement of emissions based on observation made away from the facilities. However, a comprehensive evaluation by characterizing the distribution of methane emissions at each stage of supply chain remains unclear. Here we bring together the published emissions data from the 51 methane emission studies to assess and synthesize the distribution of emissions from each supply chain to characterize the supply chain emissions. First, we combine from several published studies and obtain the data from on-site and off-site measurements. As I told before, on-site is individual emission source data, off-site reported for the entire site. And the existing literature reports emission rates in different units, and some studies provide insufficient information to allow for unit conversion. In this study, methane emissions estimates were converted into the percentage of total production, the volume of methane emitted per volume of produced gas. And the other unit we use in this study is the grams of carbon dioxide equivalent per megajoule of energy based on the high heating value. We assume the global warming potential of methane is 100 years as 27.2 based on the IPCC report, and the high heating value is 38.11 megajoule per meter cube. Methane emissions from landfill were also excluded because there's a lack of data on the amount of biomethane or biogas generation, and mainly the landfill modeling tools is used for the gas generation amount, and the emissions are based on oxidation rates as well as top power material rather than infrastructure emissions. Additionally, we also consider the emissions from switch treatment plant with anaerobic digester. We need the methane generation rate. And when we come to the data set from the literature, we divide it into subcategories. As you can see, each stage of the biomethane supply chain. The first stage is feedstock, including collecting and storing the organic materials. And the second stage is the biogas production, where the feedstock is converted to the biogas under anaerobic condition. And the possible emission sources are anaerobic digesters, buffer tank, ionization tank. After the biogas is sent to upgrading unit, the third stage is different upgrading methods can be used to generate biomethane, such as pressure swing absorption, scrubbers, water chemical absorption, chemical absorption, and membrane. And this biomethane is sent to the transmission, storage, and distribution stage. We also include the emissions from digestate storage as open or closed digestate, but we exclude the emissions from digestate usage because it's not necessary to be used in the biomethane supply chain. After we classify the data that we collected from mobile measurement studies, we need to determine the probability density function of each stage before running into the Monte Carlo simulation to assess the cumulative emissions. And the probability density function, the PDF as called, gives the good fit of emissions for each stage, considering the uncertainty assessment, and the emissions on each stage exhibit unique characteristics. They have a different probability distribution. Due to the heavy tail distribution and luck in the sample size, we use the non-parametric probability density function, which is the kernel density estimates, were generated to investigate the PDFs of each stage using Python. And the total supply chain emissions were estimated by Monte Carlo simulation, which has been widely applied to estimate methane emissions with uncertain assessment. And after each stage probability density function obtained from the kernel density estimate was defined in simulation to sample from each stage, followed by summing up emissions. And the total cumulative, we did 10,000 times Monte Carlo estimate with random draws to assess the cumulative methane emissions across the supply chain models by the Python code. Let's move what we get. After the 10,000 times of random withdrawals, adding by each stage emissions, we got these cumulative curves. On these figures, each curve defines the cumulative distribution of a single Monte Carlo, and we can say that the emissions, total supply chain emissions, range from 2.5 to 343 gram carbon equivalent per megajoule high heating value, and the median is around 41 gram carbon dioxide per megajoule. Mean is 52 gram carbon equivalent per megajoule at 95% continuous interval. As you can see in the figure, the mean emissions are higher than median. The biomethane supply chain distribution is highly upward skewed, which is the indicator of disproportionately high emitting sites, referred as super emitters. I will come to this point later, but let's look at the 50% emissions and 95% emissions is around 15, and 95% emissions is around in between 131 to 133 gram carbon dioxide equivalent per megajoule at 95% confidence interval. And when we use the global biogas and biomethane production reported by the IAE as 35 million tons of equivalent, as I mentioned before, these biomethane supply chain emissions can up to 18.5 kilogram methane per year, which is more than 2 times the higher estimate of the IAEs. IAE estimates the biomethane supply chain emissions around 9.1 teragram in 2021. Our estimate of global biogas and biomethane supply chain is significantly lower than the global oil and natural gas estimates. The IAE estimate for the natural and oil gas methane emissions is around 82.5 teragram in 2021. On the other hand, it is comparable the production segment of US oil and natural gas supply chain based on the Rutherford Group fundings. When we look at the figure B, the cumulative distribution of emission as a percentage of biomethane produced, the 50th percentile is around 2, 95th percentile is around 12.7 at the 95% confidence interval compared to the total gas production. The range in minimum medium are fairly constant across all estimates, but the low and median estimates are nearly identical compared to the natural gas, but it varies between the highest estimates. The median is around 5.1 and the mean is around 6 at 95% confidence interval, and which is higher than the natural gas. Natural gas production reported as 0.8 to 2.2% of methane production is, according to studies, 0.8 to 2.2% of methane production is released from natural gas supply chain. And we can see that the production normalized emission is considerably higher than oil and gas. This could be the variety of factors, including poor managed production facilities, lack of attention to the biomethane industry, resulting in lower investment for modernization, operation and monitoring, and as well as the employment of highly skilled plant operators when we compare to oil and natural gas. In addition to poor design, the management of feedstock and digested storage units and the limited interest in infrastructure emissions may result in emission rates compared to the amount of gas produced. Because oil and natural gas supply chain have been primarily operated by large companies for decades, they have been invested more in leak detection and repair. As I mentioned before, the cumulative distribution figure exhibits the heavy tail distribution. A small number of high emitters may cause under or overestimation of emission rates if they have intermittent emission patterns and insufficient process equipment usage or inadequate operation and management strategies. In this study, super emitters have been investigated at various stages across the supply chain, including feeding systems, substrate storage, runoff pumps, pressure relief valve on the anaerobic digester and gas holders, exhaust and aeration line of upgrading units, ventilation of units such as compressor or closed digestate tank, open digestate storage, and flaring. Since we lack information on on-site methane sources, we identify them the highest 5% of total emissions of cumulative account for 62% of cumulative emissions, which is also similar to the natural oil and natural gas supply chain distribution. Let's look at the contribution of each stage of biomethane supply chain illustrated in figure A in gram carbon equivalent per megajoule and as a percentage of total production in figure B. The distribution are almost identical. The emissions are mainly from digested storage, followed by production and upgrading stage. Results were similar. Similar results were observed by Reynolds 2017, where the highest emission come from open digested storage and pressure release valve. Similarly, Alvarez group also found production and gathering units to be the main emission source in the US oil and natural gas supply chain. Overall, the lowest emissions are exhibited in transmission, storage, and distribution stage, similar to the similar to the US oil and natural gas supply chain emissions. Alongside the on-site Monte Carlo approach described before, the whole site means off-site measurements were also useful benchmark. In this literature, methane emissions from 792 whole site measurements varied between 0.1 to 483 gram carbon dioxide equivalent per megajoule high heating value, with the average of 52, and the median is 45 gram carbon dioxide equivalent per megajoule high heating value. This is a larger range with lower median and higher limit than Monte Carlo simulation of on-site measurements, while the mean of the Monte Carlo runs is around 52, is similar to the whole site measurements, which is around 52, are comparable. The median of Monte Carlo runs are higher than the whole site data. The whole site data is a raw data. And this is the reason, the differences between is due to the heavy tail distribution of the Monte Carlo runs. And also the number of factors are known affect the measurements, including the meteorological conditions during the survey, duration of measurements, uncertainty, emission rates and calculation models, and as I told you, the presence of super emitters and process condition of facilities. It is likely to be influenced by miscellaneous sources. Let's see the figure B. On the figure A, you can see how the Monte Carlo results are distributed and compared to the whole site emissions, which is the pink box. When we come to the figure B, we can see that this small black box shows the miscellaneous sources, which can be the biofilters used for odor reduction, stored solid causing fermentation, emissions from service opening or leakage located on the top of the units, which are not quantified by on-site measurements. And we combine these miscellaneous sources as an additional emission stage to the supply chain and reassess the Monte Carlo simulation, as you can see in the figure B, pink box. And you can see that how the miscellaneous sources increase the total supply chain emissions. We found that in the figure B in figure B, we can see that miscellaneous sources could increase total supply chain emissions by 22%. To sum up, this study showed that biomethane and biogas supply chain methane emissions can account for up to 18.5 teragram per year. Although they emit less methane than oil and natural gas, the methane loss rate in supply chain exceeds those in oil and natural gas. We identified the super emitters as the highest 5%, account for 95% of cumulative emissions. We would like to highlight that those emissions can be avoided if necessary measurements are taken, and you can find more detailed information in our upcoming publication on June 17. We also mentioned the strategies how to reduce the emissions from biomethane supply chain. Given the growth in biomethane generation due to the national decarbonization strategies, more urgent efforts are also needed for the biomethane supply chain to address not only methane emissions but also the sustainability of biomethane. Here are the reference list for this presentation. You can find more references in our upcoming publication. We thank the Imperial College, Thomas Fletch and Anders French-Luce, as well as the Vanity reviewers and editors. Thank you for joining us. If you have any questions, I'm happy to answer them.
Okay, thank you, Semra. The sound was perfect for the three last slides. Sorry about that. But no, next speaker is in person here. Jarek. I use the short name because it's Jaroslaw Necki from the University of Cracovia will speak about the coal emission. And of course, it's a very strategic energy in this time. So let's go.
Unfortunately, this is very strategic energy as a resource. My name is Jaroslaw Necki. I represent the AGH University in Krakow in Poland. The Poland indeed has the largest coal excavation, hard coal excavation areas, which you already have seen today at some presentation. This is USCB, so Upper Silesian Coal Basin. The abbreviation of AGH in Polish language means the University of Mining and Metallurgy. So nowadays we don't use it anymore, as the students wouldn't really like to study at our university. So we have the science and technology, and this is much more prospectful. So I will talk about methane release from the coal mining industry, and you might think that this is one of the simplest problems which we have here today. So oil and gas sector is really complicated, the biogas as well, and coal mining is pretty simple. You have very well localized the exhaust of the methane coming out from the coal seam, and it will be very simple to estimate how much then, and all the coal mines can supply the reports about it. But it's absolutely not true. So this is even opposite, and that's why I'm here. Okay, so introduction, yeah. So introductory part is there is a lot of the definition, or during the introduction of the regulatory now, the EU tries to make a regulation about the methane emission, and they really designed it in some ways that the people might feel confused a bit about the name of the variables representing the flux. So you can really have a different kind of the variables which you can use to estimate of the fluxes, and it can be, of course, the concentration, can be area flux, flux density, the release rate, and so on. So more for the coal mine, we usually use the release rate on just or the methane release as the integral of this upper variable. And all of these variables, of course, they are measured and they have uncertainties. And these uncertainties are, when we were talking here about upscaling and the calculation of yearly release based on a momentary measurement. And this is extremely important to know the uncertainty, especially if you want to upscale it, and also to know the distribution you have. And this is the most beautiful distribution of which you can find from is the Gaussian distribution. Unfortunately, this is very rare in the science of the measurement of methane. So you heard we expect mostly the log normal distribution or RSQ distribution, but not. But taking about the measurement principle and uncertainty understanding, you can think it about these variables having the normal distribution. If you say that the uncertainty is 1 sigma, then you will just say that the 64% lies in the special between two numbers, which you have here. The example, if you assume the concentration of methane, or the mixing ratio of methane is 1.2% plus minus 0.2, it indeed means that you can expect with 68 the chance that it lies in this period. And the more important question is, what is the probability that the true value lies even beside this period? You know, so it's higher or it's lower. And then we come to the problem with the coal industry. So they are doing the measurements, and they are measuring two things: the airflow rate and the methane concentration or methane mixing ratio inside the shaft. And it refers to basically to the deep hard coal mine. So when you think about a deep hard coal mine, I mean, there is a coal seam, let's say 600 meters below the ground, and they really dig this coal out, and then they must supply the air for the people who are working down there. And they are doing with quite high flow rates, like 10,000 cubic meters per minute. So these are really huge flow rates. And then the average value what they measure, we're using the devices like this one. So these are Pellisto analyzer, which are mounted for the purpose of the safety of the people, and they have uncertainty of measurement in more or less 33% of the measured value. So 1/3 of the value is uncertain single. So you can instantly calculate that this 0.3 is really very, very uncertain. So it might be 0.4, it might be 0.2, it might be 0.1. Honestly, I have seen the real record of it, and it even had the negative value of the concentration. Yeah? So it happens in the real world. So of course, this is very nice to integrate it later on into record, and then it decreases your final emission rate. So I will tell a bit more why is it in a second. But then, of course, you try to calculate the emission rate, so release rate, and it will be this number with its uncertainty. If you assume that only concentration has uncertainty, and this, let's say, in a comparison, this is 1% uncertainty and this is a 30% uncertainty. So basically, you can skip this part in the further calculation of uncertainty. However, this is again in real science, in a real condition in a coal mine, this is also not true. So they don't know the flow rate with this uncertainty. It's again more or less 10 to 15% of uncertainty of the flow rate. So these two values are comparable final. But I would like to really to focus what we are now here for, so for the methane measurements. And then if you upscale it to the yearly value, you end up with 11 plus minus 8 kilotons per year. You might guess why I put plus minus 8. So this is the 2 sigma representation. And then if you assume that this is more or less the same input as the concentration, that you will end up at 11 plus minus 11. Yeah, which basically say that they are emitting a lot, but they might emit nothing. Yeah? And it makes really the problem when we require the reduction of the methane from the coal companies, because that immediately they can declare in any moment that they reduced any number of the emission rates any moment with the peak probability. So if you require 20% of the reduction, there is really half chance that they done it already. Yeah, doing nothing, just making the proper measurement next time. More. So, of course, the problem of this lies in law. So there is no official requirements on the making the proper, very precise analysis of the methane inside the coal mine. They are doing it, as I said, just because they are afraid of the blow up, and this blow up, which starts not from the 0.3, but more or less from 4% of methane, still happens in Poland, and the last one, very big, happens in April. And a lot of miners died because, of course, what they are doing in the everyday life, for example, they sealed this stuff. Yeah? So even if it could smell any methane, it is not doing it. So the problem of measurement, of making measurement, is that we should use the measurements which are very precise, which covers the high variability of methane. So this is not the coal mine emits all the time the same amount of methane. They dig in a different coal seams. They excavate different amount of coals. They release the pressure of the rock over and under the coal seam. And finally, there is really big variability in the fluxes. And there are very harsh conditions in the measurement place. So normally when you think about the air which is sucked from the 600 meters below ground, it looks like you have just left the normal air here 600 meters up, and then of course immediately clouds form. So the temperature falls down and the condensation occurs. And we have here, I don't know if you see it, but there is something like the smoke, but it's not smoke coming. This is the ventilation shaft chimney. And this is really the fog, I mean the cloud which goes out. And of course, if you can imagine the pellistor, especially pellistor, which is catalytic measurements, it doesn't like water. Yeah? So this is usually working in a totally wet condition. That's why the minus 0.1 is also happening there. It's not designed to work in the water. This is a very big problem, and I spent a bit of time recently to find out what could be done really to avoid making measurements in the completely wet condition, in the rain, in constant rain. You know? Normally optical instrument don't like it, the GC doesn't like it as well, the all catalytic and our metal oxide bed system also doesn't like it. So of course there is also the problem with the time resolution and the space resolution, and what the miners are doing. They are sending people's once per 2 months, and they are collecting the samples and integrating, putting into the record, somehow calibrating, and finally, as I said, they are just guessing the numbers which should be reasonable about emissions. And of course there is a dust. Completely another problem is the open cast mines. There's completely no guess about it. At least I visited 3 such coal mines in Poland, and they really completely didn't know what is the real emission. And of course the question is why? Because even basic on the tier 1, they should try to estimate some factors from the coal probes which can be drilled and taken, and they of course avoid it because this is quite expensive and you never know what happens then. It was not done before. You don't expect much methane in the lignite because this is quite shallow, and the methane probably escaped anyhow, what is not true. So basically none of Polish open pit mine, and I think the German and Czech as well in the area, do not know how much they emit the methane. And of course our proposition together with Amber colleague was to propose anything really to and there is a variety. If you go around here about the stands, you will find many really good instruments which you can try to deploy in a coal mine, especially in a deep coal mine in this maybe not very harsh condition. But you can choose whatever you want on whatever price you would say. If you want to spend only 5,000 euro, then you can buy something. If you want to spend 20,000, you also can supply some good instruments. So this is not a problem of the devices. And also the methodology. I heard here a few nice stories, and also the people are here who really can fly about the open pit mines. We can measure on the ventilation shaft on the different places. I think okay, so no, I finished. So in the scope of $30,000, you really can provide some ideas of measurements for open pit mines. We are still collecting the technology, so if you have some proposition from your side, some experience how to do it, please contact me and let's talk about it. The same is with the deep coal mine, so we could of course deploy the instruments below the condensation level, much deeper, a bit over the highest gallery input, when the air is collected from all the galleries coming down, and then you can really do the measurements here. Both the flow rates and the concentration must be done in the same place, because when the miners add a bit extra into the system, and when all this changes a bit. So this is very important to make both measurements in the same position. And of course, we can also make a tracer release. We can put the TIDLAS, open path TIDLAS, closed path TIDLAS in different places, and it can really measure with the time resolution of 1 second, with the precise of 20 ppm very easily with the instrument which is available here on the hall. And of course, the last thing which we were a bit employed for, it was this external verification of the emission, and all of these techniques was also presented here. The mass balance, which can be done in a special way, making the cross-section of the plume, the Gaussian inversion, Gaussian plumes, or the Lagrangian estimation using the different techniques. And all of these, together with the different platforms which also were presented here, can be deployed, but there will be never more precise than a direct measurement. So from my perspective, this is the very beautiful polygon for preparing the international methane emission observatory, having very nice points for the calibration of the remote instruments, because we have the coal shaft very well localized. If we will supply the very precise and nice measurements of methane emission and methane release rate from these points, then everything what will fly over, even satellite or the plane, can be really somehow calibrated on this point, and then go further and check what is our emission. So in my position, we should really start from a nice estimation of this coal mine shaft before we really go any further on. And it will firstly increase the knowledge about emission from this sector, which is completely, I would say, underestimated, and then be used in other industries as well. Thank you very much for having patience to be at the last talk.
Stay here. So we have some time for questions. So I'm waiting some. Nobody have questions?
We can dance as well.
No, we can't.
If there is no question, one volunteer.
Thank you so much for the presentation. I have a remaining question from the morning. I think it was from Joanna. So in her presentation, she showed that there is a cycle. There is a cycle in emission rate of coal in coal mining activity with 100 hours, I think. So every 100 hours it goes up and then it comes down. And yeah, so do you know why there is a this cycle?
Basically, coal mines work on the exchange of the people, so they are working in some periods of and then they had. So you can imagine if you go down there is a lot of dust, very high temperature, total humidity 100%, and when you work there. And normally they even work much shorter than normal people, so they cannot survive 8 hours working there. So the normal, they are there 4 to 6 hours and they get out. And also the travel to the coal seam takes a lot of time. And then this exchange of the people really makes not possible to excavation go all the time. And then they stop all the equipment, check the situation, check the infrastructure, and check also the all ventilation. They must build something, and so this really is like the tillage of the croplands. Yeah, so they work in exchange, and after some time they need to make a stop. They need to look at the equipment and then start again.
Other question? I got one. Oh, no.
Yes, someone? Thomas?
Maybe also a question to Jarek for these shafts now. Is a point measurement enough, or do you really want to have a measurement through the whole diameter, like you showed this transmission? Is a sensor that you place somewhere near the wall, is that enough? Is the air well mixed enough to know that you have a representative mole fraction?
Basically, this is not my idea to put these metrics of the sensor. I heard just about it, but there is planned something like that. From my point of view, if you can imagine 10,000 cubic meters per minute and a shaft which is made by 4 by 2, the Reynolds number gives you so turbulent flow rate, so there is no chance that there will be any stratification in this.
No, yeah, no, it was. Then a point measurement would be enough, right?
Yes.
You wouldn't really need...
But what I was proposing, I would really favor it open puff tidlas, which makes the cross-section of all this.
Yeah.
So even if something happens, you're covered by the whole cross-section.
It's a comment more than a question for James to thank you for the information you showed us on abandoned wells, and to say that the Commission proposal for a regulation to reduce methane emissions does include an obligation on member states to set up an inventory of these assets. So hopefully this will be useful also to know how many of these assets we actually have in the European Union, and then there's obligations to measure methane emissions and to come up with a mitigation plan to plug these wells, to reclaim, remediate the land around it. So yeah, hopefully useful for your study as well.
That will be immensely useful. Will there be a requirement for them to grant access to sites at all?
Grant access to sites to the national authorities, yes. But this information will be made publicly available, so at least that.
There is probably a problem with the documentation as well. Yeah? If some wells were 100 years ago drilled, then...
Yeah, it's a huge problem.
Abandoned wells, sometimes we don't remind where are the wells. So.
I heard some gas companies do not know precisely even where there is gas pipeline. Even. So the gas wells are probably more uncertain.
Okay. A question for me, for you, James, and perhaps Thomas. Thomas said that in Romania, when they look with a camera on the wells, you see some ground emission, and when you measure, you use something to catch all the emission, but only at the small stacks.
Yeah. So
is it possible that you have also ground emission around, or in other? Yeah.
So what they're doing is that they're also taking blanks effectively where there's no wellhead in the area, so they have a baseline of emissions from that environment, because obviously you could end up with natural wetland emissions and such like as well. So they're discounting for that.
Okay, thanks. Okay. That's okay. Thank you very much. And that's the end of the day. Rob? All right. Come on.
Just very quickly to thank both of our session chairs for a brilliant job this afternoon. So thank you very much. And thanks again to all the speakers. Thank you to everyone for the questions and for the participation. We'll see you again tomorrow morning, hopefully. And please do stay around for the drinks reception, which I think is at 4:30. I think it's in the hall. Follow me. I'll sniff out the free drinks. Okay, so thank you, everyone.